All right, this video is section 2.1 and 2.2. And we're talking about position, velocity, and speed. Speed is 11. All right. So let's start by defining position. Position is the location of an object or a point relative to a reference. In general, that reference is the origin of a coordinate system. So if we have our XY coordinate system, and here's our origin, we have a point A. If we want to describe the location of that point A, we're going to draw a vector from the origin to A, and I'll label that vector R sub A because it's the position of A. So most commonly, a position vector will be R or X. Although we often use X, Y, and Z for spatial coordinates, X is also commonly used to describe a vector, and you may even see, instead of X, Y, and Z, you may see X1, X2, X3, describing the spatial dimensions 1, 2, and 3. Right? So just some notational stuff there. The important thing here is that the position is a vector. So if we want to talk about a change in position, that's called displacement. So let's graph that. We want to talk about a change in position, then we need an initial location and a final location. I'm going to stick with my point A, and I'm going to add some point B that we're going to move to over some time interval. And there's a position vector that describes the location of point B. So what we're talking about here is we're going to move from A to B. So we can draw our displacement vector here, and I'm going to label it R A to B because we're moving from A to B. We can use our graphical addition rules for vectors here. We know that we can place vectors tip to tail and add them up. So I can say that the position of A plus the displacement from A to B is equal to the position of B, right? If I start at the origin, I can go along vector A, and then I can go along vector AB and end up at point B. Or I can go directly from the origin to point B along vector B. All right, so if I solve this for the displacement, that's going to be the position of B minus the position of A. And this is why you'll usually see it written as a delta, right? We have final minus initial, right? Which is our delta notation. All right, so closely related but different, let's talk about distance. So again, let's start with an XY coordinate system, our point A and our point B. Except now, instead of talking about the displacement, I want to talk about the distance from A to B. Let's say that A and B are 2 points on a city map. And all the streets run north and south, and I'm going to say that y is in the north direction. So I'm going to travel along one street, and then B is on a one-way street, so I've got to turn here and go down past it and come back to it. All right. So this would be my path from A to B. If we talk about distance, distance is the length of the path. So let's look at another example of how the distance and the displacement differ. Imagine you're on a basketball court and you're standing under one goal. And you run down the court and back. Well, let me change the color for my path. You're going to run all the way down the court under the other goal and come back. You return to the same point, right? So x initial is equal to x final. So delta x is 0, right? So your displacement is 0. You ended up right back where you started. But what about the distance you traveled? If the length of the court is some value L, and what's the distance you traveled? The distance you traveled is 2L, traveled down the court and back. So what this leads us to is talking about average velocity. What's your average velocity as you run down the court and back? Well, velocity is defined to be the displacement over time. And a note on notation here. We use T for delta T because we assume that the initial is 0, right? So when I take T final minus initial, that's my T of interest minus 0, and we just get T, right? So that's just a note on notation. You'll almost always see T used when you're actually talking about a time interval. If you're talking about multiple processes, you may see different times, and you need to remember that you use the time interval. All right, so let's look at our basketball court example and talk about our average velocity. So let's assume that we're moving at the same rate the whole time as we go down the court, and then we turn around and we come back down the court. We know that our displacement is 0, which means that our displacement over T is 0. And if we look at it as adding vectors, at each point on the court, I spent the same amount of time running to the right as I did running to the left. So you can see how those kind of cancel out in a nice natural way. And that's how you end up with the 0. So what about average speed? Which you may just see written as a V without a vector sign or even with an absolute value. The average speed is the distance over time. Well, the distance we traveled was 2L, so twice the length of the court covered in the time that it took us to run down the court and back, which is non-zero, right? All right, and of note here, this is a scalar quantity. It doesn't tell us anything about the direction you're moving, it's just the average speed. And this is a vector quantity. So I'm going to scroll back up here to my path that I'm taking through the city, right? So as we're moving through the city, actually, I won't scroll back up to it. I'll just redraw it. Can I copy this? Will it let me do that? Let's see. All right, let me copy it nice and easy. So let's say that as we're driving through the city, initially we're driving along this street to the east, and then we drive along this street to the south, and then we turn back to the east, and we head north to get back to our target on that one-way street. So if we want to talk about average velocity and average speed in this case, if we talk about the, let's call these something. Let's call this A, B, C, and D. So if we want to talk about average speed, that's the distance over the time. And the distance here, well, I used a D here, didn't I? I shouldn't have used a D when I'm using it for distance too. So I will write the word distance here. All right, so that's going to be A plus B plus C plus D, which is our entire length of the path, divided by the time it takes to get there. If we talk about the average velocity, remember that is the displacement over time. We'll draw this one in blue. All right. And you can see that that straight line distance is shorter. Your average velocity is going to be, the magnitude of it is going to be a smaller number than your average speed. And you can see again, we've got that cancellation I was talking about with the basketball court. For part of the time we traveled south, for part of the time we traveled north. We have portions where we're traveling to the east, but not moving north or south. So you can see how that's going to be different. All right. I think that is everything from section 2.1. So I want to put in the little bit on 2.2, instantaneous velocity and speed. Switch my pen back. I might try to be consistent on my notation here. Velocity is just a vector v, and speed is the magnitude written that way. So we defined the average velocity as delta x over t. So if we want to talk about the instantaneous velocity, we're going to take the limit of this as t goes to 0. So now just v is the limit as our time interval goes to 0 of the displacement over t. And this is just our calculus definition of rates, right? If I look at a x versus t graph, I can look at 2 points on the graph. And let's say we're interested in the average velocity at this point. I can look at this time interval, and then this time interval, and this time interval. And as I get closer and closer to that point, then I get closer and closer to that instantaneous value, right? That we know to be tangential, right? Right, the instantaneous value has the same slope as the tangent line at that point. anything else I want to say about the instantaneous value here? I guess for the instantaneous speed, it's just the absolute value or the magnitude of the velocity. Magnitude of the instantaneous velocity. That should cover everything for sections 2.1 and 2.2.